In this video, we're going to cover Fourier transform, specifically for continuous time, where the time is continuous as opposed to the discrete time. And our focus really here is to introduce the non-periodic or aperiodic system, but at the same time we're going to use it to say, yes, we can use whatever technique we came up here and apply it to periodic signals as well. Our starting point would be Fourier series, and I just want to make sure I want to write this down here because that could be a point of confusion. If you're watching this video, the assumption is that you've already watched the videos or you know about Fourier series already, and we're trying to expand from there. So if you recall, Fourier series, the requirement for Fourier series was that x of t had to be periodic, which means this had to be periodic before you had Fourier series. Okay, and the equations, if you recall, were summation of k going from minus infinity to infinity, a of k e to the j k omega 0 t, where this was the period for the signal. Once again, this equation only works if you assume that the signal is periodic. Okay, so that's great. And then of course there was a companion equation that went with this thing. It says if I have the Fourier series coefficients, then I can use it to find x of t here. But then how do I find excuse me, how do I find a of k? If I've got a x of t, we had a corresponding equation which was 1 over t, and went from, we typically write it a half a period back to half a period forward, so full period, and we'll take x of t that we had multiplied by e to the minus jk omega 0 t dt, and that would allows us to find the Fourier series coefficient from the function itself. Remember, so all of these we're reliant on the fact that the signal is periodic. Now the question becomes, what if my signal is not periodic? Then what do I do? So in that case, we have to rely on a modification of Fourier series we will call Fourier Transform. So again, this is a common point of confusion because they both start with the word Fourier. Then what is a series, what is a transform? So the requirement for being periodic is gone away. So you do not need to be periodic in order to, a signal does not have to be periodic to use a Fourier transform. That's the key thing to remember here. The rest of the process is a bit of a math work that we're gonna do to get from one place to the other. So hang on for a little bit of a math roller coaster. Okay. So now that we know the difference, now that we have created distinction between the Fourier series and Fourier transform, and know that Fourier series is limited to periodic signals only, but Fourier transform can do both periodic and non-periodic, so the requirement's gone away for that. So now what does that mean? So that basically means if I've got a signal, let's say I've got a signal that is not periodic, so let's say just some random signal here, and this signal basically goes from a point to a point, let's say from let's say if we center it around 0, we can move it anywhere we want. So let's say this signal goes from minus t over 2, or actually let's be even more general. Let's say this goes from T1 to T2, somewhere in the region. So we can do a little bit of a trick and say, look, what if we know this is not periodic, we know this is 0 going this way, we know this is 0 going this way, so it only has non-zero values here for this x of t. But let's assume this is just a period and not worry about whether it repeats itself or not. If we do that, then we can go back and grab that a of k, bring it back down here and say that is over, and let's call this piece the t, that what a t is going to be equal to the t2 minus t1 basically. Then we're going to say, okay, and then this integral is going to go from some location t1 to t2 because that's the period, x of t e to the minus jk omega 0 t dt. Okay. Now, since this is 0 from this end and that end, we could simply basically says I can rewrite this a of k as 1 over t still, but then I can go from minus infinity to infinity. I'm not changing my integral because anything outside of t1 and t2 are going to be 0, so the integral falls off. So I can write it this way. dt. So the reason I want to do this is because it allows me to just have a different representation that I'm after. At this point, I basically gonna come in and say, okay, at this point I'm going to take this this integral of jk omega 0 t dt, and I'm going to rename it. But before I rename it, I'm going to do a little bit of a move here, and that move is that I'm going to rename this piece k omega 0. I'm going to just call it an omega. So what's going to happen here, this thing is going to, I can rewrite this piece as x of, and we typically write it at this way because the variable end up being omega instead of k, because we're going to make the k not be an integer, be from a small increment, it will be a real number, let's say. If that's the case, then instead of writing jk omega 0, I will write it j omega, and that's going to be equal to integral from minus infinity to infinity x of t e to the minus j omega 0 t, no omega 0, because we replace k omega 0 with omega t dt. Okay, and so that is one of the equations that we come up. The name for this equation, this relationship, this x of j omega, is called the Fourier Transform. So this equation basically takes x of t and transforms it to a Fourier, moves it to a Fourier domain, or the frequency domain in this case, which is going to be basically x of j omega is from minus infinity to infinity x of t e to the minus j omega. We did leverage Fourier series, but what we ended up works. This equation works for both aperiodic, which means non-periodic, and periodic signals. So now, even though I have this equation, if I have a periodic signal, usually Fourier series work is easier if you're doing it by hand. If not, if a computer is doing it, then it really doesn't matter. Everybody uses just Fourier Transform. Okay. Now, so that's great. So we got x of j omega. Now the question is there any way for me to take this information back if I have x of j omega, if I have a Fourier transform, can I find x of t? Now, one thing you will notice here, which I didn't carry it far enough, But in light of the fact that we said Fourier transform was this equation, then I can go back up here and say, okay, from this equation, then I find out that A of k is equal to 1 over t x of j omega, my Fourier transform of x of t. Now, if I have that, and I have this particular equation here, then I can combine the two and say, okay, if you've got x of j omega, your x of t can be written as summation of k going from minus infinity to infinity. And remember, omega is k omega 0, right? So a of k used to be here, so instead of a of k, I put 1 over t x of j omega, or I'll just go back to k omega 0. And then e to the j k omega 0 t. I just want to make sure that you see that I'm really rewriting the Fourier series equation. All I'm doing is trying to put these Fourier transform items in it for now. So the next thing I need to do is say, look, we know that this is omega, and we know this is omega also. The only thing I don't want to do, this t we know is kind of a little bit of a bogus t because there is no period per se, but there's at any given frequency you have a different, at every k omega 0 you will have a different frequency. So what we, period and frequency. So what we want to do is we want to come back and see if we can write this one in terms of omega, and the answer is yeah, you can do that. We know that omega is equal to 2 pi over t. So if I know this and I have 1 over t, then what I could do is write this thing a little bit differently. I'm sorry, this is so this would be omega 0. There's no k here. So if I go back and kind of clean this up just a little bit, I can write this thing as 1 over 2 pi. My summation is still going to be k going from minus infinity to infinity, and then x of j omega will stay, so I'm replacing k with omega, k omega 0 with omega, e to the j omega t. Now, the omega 0 kind of gets interesting because t is headed to the infinity, right? We assume the whole from minus infinity to the infinity is a period, which makes omega 0 really small, so this will move toward the really small value, so we'll put it in here. Okay, so as t goes to infinity, omega goes to 0, right, which we represent with dw. And then if we were to work on this just a little bit more, you'll start seeing this summation, since dw is really small, this which dw would be k omega 0, then what's going to happen is that this summation x of t can be written as an integral from there's a 1 over 2 pi in the front, and then it goes from minus infinity to infinity, x of j omega, and then e to the j omega t d omega. Okay, and this is called the inverse Fourier So what we have been able to do at this point is basically take Fourier series, and by allowing the period to be from minus infinity to infinity instead of just one period to cover basically non-periodic signals, come up with this idea of Fourier transform and Fourier inverse transform. So Fourier transform will take us from the time domain to frequency domain, and inverse Fourier series will take us from a frequency domain to a time domain. One thing I want to make sure everybody notices, in fact, once we have given up on the periodic signal, you notice that the function in frequency no longer is discrete, but it's continuous. So both your function, your Fourier transform and inverse Fourier transform, both your signal in time and frequency are continuous. That's a pretty important change. So here is a summary of everything we've talked about so far. So x of t. So if I have a Fourier series of something, I can find a Fourier transform of something. I can find it in time domain. So if I have the frequency representation, I can find the time domain. And this process is called inverse Fourier transform. And then it's represented with a capital F with a -1, look like a power, but it's just the inverse of xj omega in a curly bracket. And the Fourier transform, or sometimes called Fourier integral, is set up, kind of does the reverse. It goes from time domain to frequency domain, capital F, with x of t in bracket. Now, if you want to use Fourier transform, the same equations to find Fourier series, which is Fourier series coefficient, which is basically periodic and discrete, here is a process that allows you to do that at the bottom of this. Okay, so that's more or less what we wanted to cover in this presentation. But I just wanted to take a minute and maybe do an example. Let's say someone comes to you and gives you a signal, and it says, okay, I've got a signal, and I want to know, I've got a signal x of t, okay, and my x of t is equal to let's say e minus 2 u of t. Fair enough? So somebody's giving us a signal. This signal, let's say this is in time domain, and it only has value at starting at 0, because before 0, because of u of t, it's 0, and it gets to 1, and then it decays over time. So this is the signal they've given us, and they're asking us to find the Fourier series. To find the frequency domain or Fourier transform of this. So our job is to figure out what the Fourier transform of this. We say, okay, if I have x of t and I want the Fourier transform of this thing, then it's going to be x of j omega. And x of j omega is going to be an integral from -infinity to infinity of e to the minus, oops, I forgot, yeah, that's fine. So it's e to the minus 2t u of t e to the minus j omega t dt. So if we clean this up, we notice that the only thing this is going to do, says the integral is 0 when t is less than 0, so that all I have to do to get rid of it is change the limits, and then I can sum the powers of this, so I'll have it end up with ne to the 2 plus j omega minus in front of it t dt. Just add the powers together, and one of our favorite things is taking integral of e, because it's really easy. So if I do that then and clean it all up, I'll end up with basically 1 over there's going to be a minus in front of this because it's got 2 plus j omega, and then e to the minus 2 plus j omega t, evaluated from 0 to infinite. When t is infinite, this is going to be 0. When it's 0, this is going to be a 1. So this whole thing ends up being 1 over 2 plus j omega. At this point, now you have your x of j omega, which is 1 over 2 plus j omega, and that's basically your signal in omega, and if this is 0, and you notice that this is no longer discrete, but rather is continuous with respect to omega. That's a big difference with Fourier series, which was based on the periodic signal. And so as you can see, this is a complex number. Not only is continuous, but it's a complex numbers. So we have to plot the phase and the magnitude separately if you want to plot it. But usually, for what we do, usually we look at the magnitude. So if I were to look at the magnitude of x of j omega, which basically magnitude of x of j omega is going to be 1 over square root of 4 to the power of 2 plus omega squared. So what's going to happen is the biggest is going to be 1/2, and after that it's just going to go down to actually never going to reach 0, right? So it's just going to asymptote to 0 and asymptote to 0. So my time domain signal that look like that in the frequency domain looks like that. What does that mean? At DC it's going to be 1/2, and as you flow in a direction, it's going to reduce as you go up on frequency. Its magnitude of components reduces, and as you can notice, no longer you have to worry about integer. It's just continuous all the way through both sides. That brings us to the end of this presentation on Fourier transform for continuous time and non-periodic signal, which means you can also do the periodic signal, but once again they'll end up with a lot of impulse functions, because that's how we take a continuous signal and turn it into a discrete in the frequency domain.